All right, everyone, welcome to week 18 of Kernel Dev Gardening, which is where I embarrass myself live on the internet as I learn operating systems programming. Give me a second to just test out the chat. I'll send a hello as usual. And yeah, we're going to kick it right back off today, resuming from last time. So let me bring up this. So I've been following this MIT class on OS operating systems, and yeah, last time I was working on this pagedir walk function. So I will just get that going. All right, I think that worked. Yeah. So what happened last time? So I was working on this pagedir walk function, and I didn't have time to test this last time. But that's what I was doing, and routines to manage page tables, insert and remove linear to physical mappings, pagedir walk. And that was it. So we just have to do some basic page table management, right? And this function, the goal of this function is to take a virtual address and return a page table entry that corresponds to that virtual address. And we can customize whether we want to create a page table entry if it didn't exist already. And yeah, on x86 32-bit, this is pretty simple. It's just a two-level paging mechanism. So just two tables. And yeah. Let's see. The page table might not exist yet. If it didn't exist, and create is false, return null. Otherwise, allocate a new page table with page alloc. If the allocation fails, return null. Otherwise, increment the ref count, make sure the page is cleared, and then the function returns a pointer into the new page table. And then there were some hints. And then just to walk through the code I had written, so it's all about unpacking various parts of the virtual address, and we had some macros. Can you share a PowerPoint of teaching? Hey, Nithaji? Honestly, I'm not quite sure what you mean. What I can show you is this URL to this MIT class, which is what I'm following. Hey, Yusrina. Thanks for joining. Yeah, so it's all about unpacking different parts of this virtual address, which I have some macros to do. Yeah, page directory index is this part all the way on the left. So we just need to shift 22 bits over to get that. Page table index, we need to shift 12 bits and then mask off the low 10 bits, which is what we're doing here. For the page offset, we just need to mask the low 12 bits. Nice. So we got the page directory index, got the page table index. And then now what we're going to do is take the given page directory and compute a pointer to a page directory entry. I'm just kind of thinking if this is named correctly. It's not the page directory entry itself, it's like a pointer. I'm just going to name it like that for the moment, to clarify that. Right, and then we dereference that pointer to actually get a page directory entry. And then we're going to shift that over 12 bits. Excuse me, I have a bit of a cough. Yeah, so then we get a page directory entry. And in the upper 20, how many bits is that? It's like upper 20 bits, I believe. We have the address of a page table. And that's what I was trying to get. Because the point is to check if we need to create a new page table or not. And so dereference the pointer, get the page directory entry, shift it over by 12 bits to get the page table physical address part of that entry. Then I'm gonna I'll also take the chance to just move this a bit higher to the top. And while I'm at it, I can also make a bunch of stuff const, which I didn't do last time. Pretty much everything here can be const. Although in the future, I might actually try to mutate the page directory entry via this pointer, so that's not const, but then this is const. And then it's time to check, okay, is the page table physical address 0 or not? And if it is 0, that means we don't have a page table, so we need to make one. Otherwise, that's a bit of the simpler case. If we do have a page table physical address, which meaning if this pointer is actually valid, that this is the specific pointer we're talking about right now. If this pointer exists, then that's this thing. And so if it exists, meaning it was not 0, we then, let's see, we convert it into we convert it to a kernel virtual address. And we need to do that because basically the kernel cannot work with physical addresses, because at this point we're totally operating with virtual memory enabled, and so we need to take that physical address, convert it to the kernel virtual address that maps to that physical range, and we do that with this macro, which is actually pretty simple. All it does is take the physical address and then add the current base offset, which is I believe only possible because we're assuming that there is less than, like, we're assuming a pretty small amount of physical memory. We're assuming like definitely less than 256 megabytes. More realistically, the VM is currently running with 128 megabytes, which means there is enough space. So this top section is the current base region. It's this 256 megabyte space, virtual memory space, where the kernel is mapped, and we can fit all 128 megabytes of physical memory into this region, which means we can use a trivial addition for the conversion. Right, so we take that physical address, convert it to its kernel virtual address, so we can manipulate and work with it from the kernel's like C code, and that is going to emerge as a page table, a VA, virtual address, which is a pointer to a page table entry, or rather an array of page table entries. Then next, we're going to take that and use that as a base into an array, and then add our page table index, which we computed all the way up here. And I mean, technically, oh yeah, the reason it's up here is because it needs to be used in both branches. Although this code could maybe even be refactored out into the bottom here. But for the moment, I'm not doing that. So yeah, so we take that base pointer, compute a pointer to the actual page table entry. And then we simply return that. We set the ret to that pointer and then return that. So that's the happy case. That's the easiest case where with the address and the page table is already existing, and we just kind of we find this thing, we walk down there, find this thing, and return the pointer to the page table address. In the unhappy path, and I'm also just kind of repeating this to help myself remember what I did last week and kind of get into the mind state for getting back into working on this. Then what about the unhappy path? So what if, what if the page table physical address was 0, which means there is no page table yet? Next, we need to check the create argument. So if it was false, we go to fail, meaning we just return null. Otherwise, it's time to create the page table or allocate the page table. So we page alloc, which is our memory allocator, our very simple memory allocator that we wrote a couple weeks ago, and we're going to ask it for a new frame of physical memory, which we're kind of representing via these page info structures. And we're also requesting for the memory to be zeroed out. So this is going to return to us kind of like, I kind of consider it like a bit of like a token. Like this struct page info pointer is kind of like a token that represents a frame of physical memory. It isn't directly that, but it is this kind of token that represents one. And you can get one from the page allocator, and you can also give it back when it's time to free it. That's how it works. Sorry, page alloc, page free. Yeah, to give the frame or the page back, you need to return this token that you had previously received from the allocator. But we also need to check if that succeeded, because it might be the case that we're actually out of physical memory. And so if that was null, we go to fail. I just noticed that my text is kind of overlapping with this chat thing. I'm just going to try to fix that real quick. Chat box. Move that over just a little bit. I'm still a little bit new to that. Okay. Now it's not overlapping as much. Hopefully that should be more clear. Okay. Right, so now, okay, if we survived all the way here, we really have a frame of physical memory, and we increment the ref count on it, because that's what we were told to do up here. Apparently that's how that works. And then now it's time to actually try to do something with this. And specifically, what we're trying to do is set this pointer. So now we got our page of memory, which is going to be our page table. And we need to point the page directory entry to point to it. But it's a physical address, or at least I'm pretty sure I'm pretty sure it's a physical address. And the reason I say this is because in the manual it says the word physical address here. So I'm pretty confident that we need to set the pointer here, but it's going to be a physical address. So that's what we do here with this macro, page to PA, which I think it just does a subtraction. No, it just, yeah. I think I explained this last time. It computes the index and then applies a page shift to really get the physical address of the page. So now we have this new page physical address. I added an assertion because I felt that was important, and because eventually I'll be actually relying on this right here when I OR in this into the page directory entry copy. I mean, this whole thing is kind of a bit of a to-do. I'm being a little bit overly verbose with how I'm doing it right now, with like making a copy, mutating the copy, and then assigning it back in. I think I could do this entirely with like one line of code where the dereference is on the left side of the OR equals. But for the moment, I'm just going to leave it like this until I am sure this works. Hey, Dhruv. I hope I said that right. Hello, I also want to start with kernel development, or want to just, I can't read it, the heart's in the way. A gist of it, can you tell me how you start? Yeah, absolutely. So I'm not an expert. And all I am doing is taking this class. It's this MIT class. I'll just post a link to it right here. I am self-studying this operating systems class from MIT in order to learn this stuff. You can find all of my previous streams on my YouTube, but I wouldn't recommend watching like the first like I wouldn't recommend watching a lot of them because I was doing the wrong thing. I would only recommend watching from week 13 on, which is when I switched to this thing. Before then, I was looking at this operating system called x86, which ended up not being a good fit for me because it had too much already. But if you're a bit more of a beginner, then I would recommend reading through x86 and just doing some basic reading through the code to see what you can understand. And also read the x86 book. And then maybe when you're ready, you can move on to doing the same thing that I'm doing, which is following the exercises to build your own OS from this more minimal foundation that they provide in the class. Right. And anyway, so we get page directory entry copy. We OR in the bits of the new physical address of the new page. Also asserting that the page has the low 12 bits set to 0, which should be true because the allocator at this point only operates on page boundaries. We can see this page alloc. Actually, I guess it's not super visible here, but each of these struct page infos corresponds to an entire page of memory. Yeah. Anyway, I'm pretty sure that's true, but I haven't actually run this code yet. So we will do this in one moment after I've just kind of refreshed myself. So now we OR in the bits into the page directory entry copy, and then we reassign it back into memory via the page directory entry pointer, which we computed up here. And then what we need to do is actually get the page table entry. But wait, there's a couple things involved though, because first, up to now we've been using the physical address of the new page, and that worked fine because that's what we needed for the page directory entry. But now we want to actually return a kernel virtual address, and so we need to do page to kva on that struct thing, which all it does is it takes the page info pointer, gets the physical address, and then runs it through the kadder to get the kernel virtual address. When I like rewrite this all from scratch, I'm going to try to do a better job with this naming, I think, or find some way to make the naming more clear, because personally I find this very confusing. Why they're like, some things are macros, some things are in static inline functions, this thing is all uppercase, you know, stuff like that. So I think I'm not totally happy with that. But for the moment, I'm just using what was provided for the class. Drew, yeah. How do you configure the development environment? I know in the course they're using Linux, and they are assuming x86 32-bit. I don't have it. Yeah, it's a little bit annoying, but it wasn't like that hard. I am obviously on Mac OS right now. I'm not even using a virtual machine. I'm like, well, I mean, I'm running the OS in an emulator. I'm using Qimu to run it, but also all of the support for that was provided also with this JOS operating system. You do need to figure out a couple annoying things, like getting the tool chain is kind of annoying. I'm using this like i386 ELF tool chain. I think it's from New OS or something like this. But it wasn't like, it was a little bit annoying, but you should definitely be able to figure it out. And it's a good learning experience to do that anyway. But yeah, if you want to join my Discord, I'm happy to chat more about that topic later. Yeah. Let's get the page, and then I get the virtual address of that piece of memory. So we're taking this block, which we formerly only had a physical address pointer. Now we take that and get a virtual. We convert that to its virtual address pointer. And then we just add our index to get the page table entry pointer. And I'll just call this pointer. Oh, wow. Apply. Yeah. Page table entry pointer, and return that. So that was my best attempt at doing this. And now first I'm just going to do a quick commit, because I just want to commit all these like little things that I did. Yeah, it's like, and ultimately I would probably rewrite all of the commit history, but I'm not so focused on that right now. I'm just focused on moving forward as much as possible. So clean up. doing it a little bit sloppily right now. Right. Okay, so I just explained a bunch of code. Now, the question was, I kind of don't know how to test it. The way I've been moving forward. Okay. 20-second break for standing up and stretching. Be right back. Okay. Let's see. So they... So I've just been working my way through this function in a minute and moving this panic line down as I implement more and more support, but I kind of forgot. So last time I was implementing these things. Check page free list, check page alloc. And I did both of those. And if we run the kernel, check page alloc succeeded, and then it panicked at line 188. I hope that's right. Yeah. So what's in check page though? Oh, did I? Maybe I'm not ready to move on. I didn't actually realize this. Page insert. But did I already do that? Page insert. Oh, did I? Wait a sec. I see. Was that part of the... So is that part of this current thing? Yes, okay, I see. So I'm not ready to move on. I can only... Right, okay, so after I implement all these functions, I can then move on to running this thing and seeing if everything works. But that is actually a lot of code to like blindly code, I think. I wish there was a way I could test this a bit more in isolation. It would be really cool if I had some kind of like unit testing infrastructure or something like that, but I don't at the moment. Is there any, like, is there any way I can extract this out? Like, I just literally don't have any infrastructure for taking pieces of code and like instantiating them in like a smaller environment that's just not the entire kernel. I suppose though I could just like really just hack it and write a few tests of my own right here, because I can, yeah. I could make a page. I mean, that's kind of how we're doing things anyway. We're just putting our unit tests directly into the production code of the kernel, which is kind of a simple way to do it. Maybe that's just worth... I feel like that's worth trying, writing my own little test. I don't need to spend too long on it, maybe. Also, I've already spent half an hour and I haven't done anything. So, on second thought, no, I'm just gonna say screw it and keep moving on. Boot map region. If I had unlimited time, maybe, but for the moment, I'm just trying to make progress And I hope that doesn't come back to bite me later. Okay. The TA solution uses page walk. Map VA, V plus VA plus size of virtual address space to physical range in the page table rooted at page dir size as a multiple of page size. Size is a multiple of page size. Okay. And VA and P are both page aligned. Use permission bits perm or PTEP for the entries. This function is only intended to set up the static mappings above utop. As such, it should not change the PP ref on the mapped pages. Boot map region. Okay. I think I kind of need to understand what utop is. Okay, utop. Maybe I don't actually need to. I still am very fuzzy on all of this. Wait a sec. What was current base again? How many zeros were there? It was like 7 zeros. F0, yeah. 0. Okay, I think that's 7. That is also 7 zeros. So that's current base, right? That's this is remapped physical memory, but isn't also the kernel itself there? Yeah, it's like, yeah. And then what? And then there's a bunch of other stuff. But yeah, these are more of those permanent mappings. Okay, whatever. I think that's actually not that important. Time to write some code. Okay. It's a void function. So we're trying to map a region. Yeah, we're trying to map a region of virtual memory to make it resolve to a region of physical memory. Okay, size multiple of page size. So let's say size is going to be something like 1 page size, 2 page size, or whatever. I might even add an assertion on that. Size, just to check that on the way in. Page directory. And apparently we get some permissions there. Okay. So I'm just gonna like make some like little test cases for myself to kind of break down the work I need to do. So let's say it's like a easy, like simple case, 1 page. Then it's like complex case, 3 pages or something like that. 1 page. Okay, we get simple 1 page. Maybe I'll just start off. Let's assume it's just 1 page. That means we're going to set one page table entry. So we can use our fancy PTE walk page dir walk, and we're going to pass in, I already forgot, so it takes a page directory virtual address, and whether we should create or not. It's interesting. And so naively, I'm going to say something like this. This is probably not going to compile. That's my guess. Because for casting, we need to maybe even this won't compile because I didn't make it const. Okay. But yeah, you can have a non-const thing and pass it to a const function. I think that's totally fine. Although this is a const to the void, or it's not a const on the pointer, it's a const to the void anyway. So okay, so we can, let's say we did this. That means but then what if this was 0? Like, what if that failed? There's no way to report a failure. So, time to assert. In the absence of anything else, I'm just going to add some assertions. Why did I do this wrong? No, it's just a bit slow. Okay. So we're going to try to allocate, and we're passing our convenient create equals true. So we're guaranteed to get a page table entry pointer. And that is kind of a lot of the hard work. And then once we can just assume we basically have one of these things, and then all that's kind of left to do is point it where it needs to go. And properly honor all of these bits. So, yeah. Again, I'm just focusing right now on the one page. Like, the code I'm writing is not going to work for this case where you can pass an arbitrary size, but I'm not worried about that for the moment. I'm just trying to get the base code working. And yeah, I think unlike last time, I am going to do this more slightly terse format, where now I'm mutating the page directory thing, and what do I want to do? Also, there is a few other things we could assert here. VA and PA are both page aligned, so VA, PA. But did I do this? Page size is what, 4K or whatever? Yeah, I'm pretty sure I did it. So yeah, so pretty confident that we're checking that these things are all page aligned. Which would mean something like this, I feel like, because we're trying to set, we have this page directory entry, and I'm just trying to set these bits into it. Address. Let me open my incel manual. This was the documentation about the page directory entry, but yep, no. That references a page table format of 32-bit page table that maps it for 4K page. Okay. Just to have all the documentation in one place. All right, I totally can't read the name, but hello. I can read Chinese a little bit. I think that's the Wu character at the end, but hello. Yeah, let me, okay. So anyway, the important part is it says physical address of the 4K page referenced by this entry. Page frame. And when it says address, like the tricky thing is it's not the full address because that would be 32 bits. It's only like the frame number, because then the 12 bits are reserved for the offset. So, yep. So here's what, yeah. So since we've already verified that the low 12 bits are 0, search and found with 50 U's, brew install. Yeah, that looks right to me, Dhruv. I think I used a different one because I started with x86 and there were some different instructions, but yeah, probably that's the one that works just fine. Nice. So we put in the physical address, and then now what? We need to respect the permissions or something like that. It says use permission bits perm or PTEP. What is PTEP? Present. Okay. But what is perm though? So the bits, like, also interesting. What is a 1 here? Actually, I actually kind of didn't know that. Present. Oh, okay, I see. Okay, that's the present bit. Present, read, write, user, supervisor. So these are probably going to be supervisor pages, almost certainly. But page level write through. I don't know what that is. Page level cache disable. Don't know what that is. Accessed. These are those accessed and dirty bits, which the CPU sets. Don't know what pat is. Don't know what the global thing is. Ignored. Okay. For us right now though, so we definitely need PTEP. But I think in order to really understand this, I need to see how it's used. No. So we've done so. In fact, we can now memory using page insert. Okay. But I don't, why, okay, I don't see any callers because I probably need to write the caller. So I'm in control of that, I suppose. But yeah, okay, given that I don't quite know what to do, so here's my guess. My guess is that perm is just going to be a combination of these various macros ANDed together, ORed together. these are the things that correspond directly to like the documentation I just read. And so I think we're just crafting like a number basically. And just for fun, I'm going to do that on a separate line. I don't think that needs to happen on a separate line. I could also like OR it all into like one massive thing. But for the sake of early like debuggability, I'm just going to do that like this. 20-second break. All right. So we are ORing in some more bits. I'm just doing what it says. Okay. It says don't change the pp-ref on the maps pages. Okay. So I'm just going to stage this as like a little checkpoint. But yeah, that's what I have so far. We use this nice function that we already got to get the page directory entry pointer, and then all we do is like set some bits of where we want it to point to and what the permission is. So I think that works for the simplest case of one page. Now, let's say I wanted to do this with an arbitrary number of pages. Let's go harder case, 2 pages. Okay, let's say I'm doing this. There should also probably be some limit on the size that can be mapped or something like that. I don't really know. I wonder. So this represents the amount of, it's like measured in bytes. And clearly there's going to be some limit to that, but I don't know what that limit would be. But clearly we cannot support arbitrary sizes, because at some point this is going to fail. And maybe, I don't really know what the intended I don't know what the intended behavior is. If, like, what happens if we're trying to map some region of memory, but we run out halfway? It would be nice if that like completely just rolled back everything. That's definitely not the easiest solution. Like the easiest thing to do is just like do a bunch of stuff and then just exit and kind of leave things in like a half initialized state, I guess. But yeah, so I don't know enough about this whole thing yet to really say what a better solution would be or how I would, what that would be, but I'm just going to ignore that for now. Let's get back to the specific problem. Let's say we wanted to support a size that's 2 pages, okay. So we're probably going to need a loop. I'm just going to preemptively make a for loop because I'm getting the vibe that we're going to need a loop. And the number of iterations, it's going to be like num pages, constant num pages equals size page shift, right? Something like that. Because size is literally going to be like a page size type of number. Ah, shit, but, wait a sec. Hex, it's like hex 1000, right? Right. And so if we shift that 12 bits, we get 1. So I think that's what I want. So we're going to just go through. So for every one of these, we're going to do an iteration of the loop. And I'm just going to like quickly copy this, comment this out. Okay. And this I is going to be, like the real name of that variable is, I think it's like page index or something like that. Page index. Oh, what the, ugh, I did not. I don't know what happened. All I wanted to do was rename all these I's to page index. To be a little bit more clear. And so for everyone, we're gonna, this stays constant. So now we're, yeah, so now the VA needs to be different. And t page VA equals VA plus something like this. I'm like a little bit guessing right now, but I think it's something like that. Because we have, like, the VA is more kind of like the base virtual address, and we want to be adding, like, you know, for on the first, maybe a visualization will be good to do just to help work through it. What would be the best visualization of this? I don't know. I'm just gonna, so I'm just gonna do this. Oh, okay. No, I did not mean to do that. I want a black border. Okay. Can I, okay, let's say this is our very kind of rudimentary picture of this. VA points here. And so this is going to be like num pages, pages equals 3. And then our page index is going to be it's like 0, 1, and 2. And so it's like this is going to be VA plus 4096, for example. And another way to do this is page shift. Yeah, I'm pretty sure that's right. We just need to convert. convert the page index back into like a memory offset, add that to the virtual address, which is a uint pointer t, which is kind of a weird number. To be using for this. But I think it is correct. I think that will work. So then we get our page virtual address, which we can then pass into here. True. I'm going to keep the assertion. I think maybe eventually I will change this to just bail out. Boot map region. I think I'm going to, based on the naming of this, I kind of get the sense that this is only used during the boot process. So I'm going to keep the assertion. Yeah. Just for a quick refresh, what situations does this return null? I'm never passing false. It's really only if the thing failed, so yeah. So we compute this virtual address based off of this thing. And then this is like wrong. Fizz energy is what? Unit 32T. Page PA. Something like this. Like anywhere we were previously using VA and PA raw, we need to not do that. Okay. But I think that's like sort of it. Num pages, so size. It's just like 1K, 2K, 3K kind of thing. Or no, one. It's like 1 page, 2 page, 3 pages, but it's like 4K, 8K, 12K. Get the index. Let's say I want to allocate 8K. Yeah, then that would produce a 2. Okay. On pages, then we do some iteration for each page index. We get the I'm just gonna call this like offset from base equals page index equals page shift. Offset from base, just to like, or set from base. Okay. I kind of tend to make things ints by default just because it's simpler and you can like assert them and stuff a bit more easily, but I don't know. For the moment, I'll just make this a unit 32T. Yeah. Question: does this compile? Yes, it does. Great. Const also from base. Page VA. I mean, technically this can be const 2. This cannot be const. Well, it can be const like here or something like that, but const. Okay. Anyway, so we got the offset from the base. Then we just add that offset in bytes. No like pointer or arithmetic to worry about. This is like a uint pointer t. This is a phys t, which is just the uint 32t. So we're just safe to just do plain addition, basically. Page VA, walk it, get the page table pointer, make sure it's not null, and then get the page PA, physical address, offset from base. Page PA. Okay. I think that is like sort of right. Kind of just like keeping this comment around just to see the original version of the code. Just for reference, I can delete that later. Boot map region. Right. All right, doing some coding. I'll take a quick moment just to like plug myself. I have a Discord. Feel free to join the Discord if you want. It's very friendly, very casual. Not too many people in there right now. And yeah, like and subscribe or comment, you know, if you enjoy what I'm doing. Thanks. Moving on. What's the next function? Page lookup. Okay. PTE store. Huh. Okay. Interesting. Return the page mapped at virtual address VA. Page mapped at virtual address VA. Return the page info. Yeah. Return the page info. If PTE store is not 0, then store in it the address of the PTE for this page. This is used by page remove and can be used to verify page permissions for syscall arguments, but should not be used by most callers. Oh, interesting. Return null if no page mapped at VA. Hint, the TA solution uses page walk and page to PA. Okay. Return the page mapped at virtual address VA. So what's going on? So coming back to our trusty diagram. So we're given a virtual address, and the idea is to get like basically resolve it to the physical frame and even return a page info returning the corresponding page info. PA to page. So maybe let me guess how that works before I look at the answer. So we are given a physical address, and we need to respond we need to return a pointer to a page info, one of these page info structures. In order to do that, well, hopefully, like, is it aligned? Wait a sec. Is it aligned? It might not be aligned, but I think that doesn't matter. But it would be nice. Virtual address VA. So let's pretend it is aligned to keep it simple. We're given a virtual address. We can convert that to the physical address by subtracting the current base offset. And then we need to get the index of the physical frame. So we can do that by shifting the 12 bits to the right. And then using that index, we can add that index to k pages and then get a pointer to this thing and return that. That's my guess. Let's see the answer. So given the PA page number, oh wait, okay, I was kind of confused, but anyway, 20-second break. I'll be right back. Okay, yeah, in the explanation I just gave, I was starting with a virtual address, but in reality, this particular function starts with a physical address, which is even easier. So all we need to do is get the index, get the page number, which we do by shifting by 12 bits, and then we use that as an index from K pages or G pages. I think I renamed it to G pages. And then returning the pointer. That's exactly what I just said. Yeah, cool. Okay. Fill in this function. Okay. So given a virtual address, so page dir walk, page dir VA, I think false. If PTP equals null. Okay. So we want to like query for the PTE, but in this case, we're not trying to create it if it exists. If it doesn't exist, we just want to know about that and then bail out, which is our first sign that there's no page mapped. But otherwise, if there is a page table entry pointer, then Junior, awesome, thank you, thanks very much. If we do have a page table entry pointer, that means we have like a valid one of these things, which we can extract out the physical address. Hi from Africa, Senegal. Awesome. My good friend Amat Kama is from Senegal. I'm just gonna quickly, yeah, he's awesome. He's like a sick security researcher. Follow him on Twitter. Yeah. Oh, all right. Whatever. Yeah. Aces, offensive con. Anyway, yeah. Thanks for joining. Okay. Constant phys t pa equals ptep page, or it was like ptx or something like that. What page? I'm just I'm just using page shift all over the place as something that represents 12, and that gets the there's probably these other functions I can use, like page. Oh, I don't know. I'm just kind of like doing it from scratch. Wait a sec. No, like, or what I was kind of thinking was like, okay, first we have this thing. We like shift it all the way over 12 bits to get the frame number, but ultimately what we actually want is a real physical address. So we can shift it back, but what I can actually just do is like I want to like and away. I actually don't know if that's correct. I think it might be. I I think that's correct. I'm not totally sure. I also kind of don't care, and so maybe I'll just do the silly thing, like the really just dumb thing, and shift it to the right, and then shift it back to the left. To like I'm a bit more confident because I kind of I'm not super fresh on all of my like bit twiddling and details and stuff like this. I kind of don't know what type by default it is, and like how many bits, like what that produces and stuff. But I don't know. I'm a little bit more confident in this like kind of silly thing. I know that if we shift it all the way down, we can get rid of everything, and then we shift it back up, it should fill with zeros. And that gives us the, and then PA2 page, right? We were just looking at this. This gives us a page info. Page info. Okay. Okay, is that right? I'm not doing any of the storing stuff yet. Yo, Ismail. Am I saying that right? Is it Ismail or LS Mail? Because it looks like LS Mail also. But yo, good to see you. Thanks for coming back. Hope you had a good week. I want to add an assertion. Assert that PTE P wait, what? No. I basically want to make sure. Yeah, no, I want to assert that this is real. That this starts with an I. Okay, awesome, great. Thanks for clarifying that for me. I want to assert that the physical address exists. Unless that assertion could actually fail if we are mapping the zero page. Interesting. Because in that case, we would legitimately have a page table entry with all zeros in the bottom. I don't know if we're planning to do that or not. Personally, I don't want to be mapping the 0 page like ever, so we can catch like null pointer dereferences and stuff like this. So I'm just gonna add, so I will add a comment. This might be if the 0 page is mapped, this will assert wrongly, or something like that. This will, it shouldn't. Okay, let me put that on a new line right here. Okay. Wow. Okay. Taking a drink of water. So I kind of did a bit of this, but PTE store. If this is not 0, store in it the address of the PTE for this page, which we looked up right here. If PTE store equals okay. I think that's like kind of correct. Return the page mapped at this virtual address. If this thing is not 0, store in it the address of the PTE, which I don't know if there's no page map. So we like walk and try to get the PTE for all of this stuff we don't want to create. If it returned null, interesting. What should this thing what's the valid status of like this thing if this thing failed? Should we were to put a null in there too? I kind of don't think so. In my opinion, if this function returns null, you know, don't assume that we did anything here. Okay. Otherwise, we got a real PTE. So if this thing is legit, then store in it our PTE pointer. Then take the actual page table entry, zero out the low 12 bits, and to produce a real physical address, which hopefully should not be 0. And then we can get the, get the page info and return that. I think we're good. I'm going to, it's so, like, I can't run any of this quite yet, I think, but in it, what's it called? Page lookup. Okay, moving on. Page remove. Let's see. Are you working on memory management? I am moving on a little bit. Yeah, I'm working on actually virtual memory right now. So like a couple times ago, I was working on all this physical page allocation, physical page management. I think you would have been there for that. And now, now that I finished that, I'm able to move on to the next part, which is using that in order to implement virtual memory. Because in order to implement virtual memory, we need to allocate page tables and stuff like this. And so now it's kind of the next step of this. Page remove. unmaps a physical page at virtual address VA. One second. I feel like my my chat thing in the stream is not working because there's like a bunch of chat activity, but it still is like the first two chats of the day. I feel like it's too bad. Ugh. Oh well. I wonder what happened there. All right. Maybe I'll fix it for next time. Page remove. Unmaps the physical page at virtual address VA. If there's no... one second. Indeed, it's not. Yeah, it's like disappointing. Is there anything I can do right now to just like fix that or something? I don't know, I'm just kind of dragging it around. Let me quickly check Streamlabs, which is what I'm using for like that chat box thing. Hopefully it shouldn't take too long. Chat box. Okay, I think, no, I'm not going to, maybe the overlay is frozen. Yeah, I'm not going to worry about it. I'm just gonna keep going. Hey, Prince. All right, let's move on to page remove. Unmaps the physical page at virtual address VA. If there's no physical page, silently does nothing. Details. The ref count should decrement. The physical page should be freed if the ref count reaches 0. Page table entry corresponding to VA should be set to 0. The TLB must be invalidated if you remove an entry. The TA solution is implemented using page lookup TLB invalidate. So this is like I kind of know what the TLB is, but I'm very much not familiar with like all these details of when you need to invalidate it and stuff. But whatever. Page deck ref. All right, let's just so page lookup is the one that I just did. Okay. Unmap the page at virtual address VA. All right, first page deck ref. All this does. Oh, that's pretty easy. Did I already do this though? Yes, I did this. Page free. So that is super nifty. Hey, it is possible to hack into remote servers. Yes, it is possible to hack into remote servers. Are you interested in hacking into remote servers, Prince? Okay. I'm just going to do some coding. Page info equals page lookup VA. There was something else here. PTE store. I think I will need this. So let me, PTE, PTE 0 or something. What is it? This is just an int or something like that? Okay, yeah. And we get this, and then what if page info p equals null? Oh shit. Right. My college have a college app on Google Play Store and to access our study material and other stuff. Yeah. I mean, I wouldn't really recommend hacking your college. But what am I trying to do again? Unmaps the physical page, blah, blah, blah. There's no physical page, do nothing. So if there's no physical page, go to fail. Okay. Otherwise, we have to put a set of passwords so it's possible to hack into it. Yeah. All right, 20-second break. Okay. Prince, I think you're getting yourself into some trouble there. I would not recommend hacking your college. What I would recommend is learning how to write an operating system. JK, I am 50. Okay, what are we doing? Unmaps the physical page. The ref count should decrement. So, page fo p. No, I'm not German. I do live in Germany, though, but I'm not German. Okay. The ref count should decrement. The physical page be freed. I'm just going. I don't totally know the order that should happen here, but I can clean that up later. Decrement the ref count. Wait a sec. I'm stupid. No. Okay. Call page dec ref, which takes care of decrementing the ref count and also calling page free. The page table entry corresponding to VA should be set to 0. PTE. Oh wait, oh I did this wrong. Okay, it's a double pointer. So PTE, and then I can say PT equals 0. TLB must be invalidated. How do you invalidate a TLB? Flush the entry only if we're modifying the current address space. meaning the current address space is the one that's currently loaded into CR3. But for right now, with the kernel, like we only have one page directory, we have only one address space, so we're doing that all the time. And apparently there's some instruction you can run that like does this, just out of curiosity. Okay. Right. Invalidate TLB entries. Invalidates any with the source operand. The source operand is a memory address. The processor determines the page that contains the address and flushes all the TLB entries. So the TLB, what's the TLB? The TLB is like a cache of the page table entries. I totally forget like more details about how it works. I know conceptually it's some kind of mapping between virtual address and physical frame, something like that. So it probably takes in a virtual address, I'm gonna guess. Okay, I'm not gonna care about that too much. Okay, yeah, virtual address. So apparently I'm supposed to call this or something. Validate page. Wait. Why? Shit. Why is it necessary to? For the moment, this is not used. Okay, it's like a. Okay. After wasting time on 4chan, recently learning mathematics, any advice? Yeah, I am totally not the right person to ask about this. I'm not that good at, not really that good at mathematics, which luckily is not required for operating systems programming, which is why I'm doing this. Wow. So yeah, unfortunately I cannot advise on that, but maybe somebody else that's watching can. If you remove an entry from the page table. So, right, so like literally this is the action that removes the entry from the page table. So maybe we'll kind of like put these a little bit more tightly together. Because we literally just don't have a mapping. That mapping is not there anymore, so we need to like invalidate the cache, which is exactly what we do. Okay. Silently does nothing. So there's no physical address there. That means, oh, wait, what? If there is no, wait a sec. There's no physical page at that address. So we give an address. We try to look up a physical page corresponding to it. And that's what should happen here. But if there's no, so one would have, like, what's an example of an address where there's no physical page? That's like literally any address that's just not mapped. So for example, going back to our diagram, like, yeah, like say anywhere, you know, for example, nothing here is mapped to anything. Or maybe the easier diagram is like, it's just this thing to always keep looking at. So let's say we have an address, but it just like it points to a page directory that just doesn't map to anywhere. That means the page tree walk is going to fail. We're not going to get the PTE, and just like literally nothing is mapped. So I think that works. Physical page should be freed. So these two things happen together with page decref. Page table entry should be set to 0. Which we did. I think we did it. So no way to tell if it works. I can't run the code yet, but init page remove. Am I streaming somewhere else too? No, I am only on YouTube. I'm exclusively streaming on YouTube. Yeah, and I tried it on Twitch once, but I didn't get a lot of people that joined, and also the video like disappeared on me after a couple days, and so I've just been on YouTube ever since. Okay, and okay, page insert. That would be super cool if I could finish this today. Okay, insert. Okay. Map the physical page at virtual address VA. The permissions should be set to perm PTEP. Requirements, if there's already a page mapped there, it should be removed. Page insert. If necessary, on demand, a page table should be allocated and inserted. Yep, okay. This is like a pretty high-level function, high-level API. Given page info and somewhere in virtual memory that we know we want to put this, just make it happen. Just make it happen. Okay. Ref should be incremented if the insertion succeeds. So it must be. No, thank you for the subscribe. Kind of. Komotso. Thank you for the subscribe. To be incremented if the insertion succeeds. Right. TLB must be invalidated if a page was formerly present. So it kind of is related to this thing. Corner case hint. Make sure to consider what happens when the same. Thanks, Junior. Make sure to consider what happens when the same PP is reinserted. What? When the same PP is reinserted at the same virtual address in the page dir. However, try not to distinguish this case in your code, as this frequently leads to subtle bugs. There's an elegant way to handle everything in one code path. Man, okay. Turn 0 on success. Fail. Return E, no, mem. All right, I'm pre-set up with my with my fail path. Okay. Page to walk, page remove, and page to PA. Okay. Okay, I am still kind of wrapping my head around the task here. So given a PP, physical page, and a virtual address, map it there. Okay, if there's already a page mapped there though. Okay, as usual, I'm just going to start coding and see where that leads me. So page dir VA create. But wait a sec. If there is already a page mapped there, it should be removed. Which I just like implemented, right? Page lookup. So this one is where this one was used in service of implementing page remove. And the page remove is when I'm trying to remove a virtual address. What's the physical address of virtual? Okay. If the insertion succeeds, CLV must be invalidated. Man, this is like so. It feels complex to me. There's like all these requirements. There's this corner case to worry about. Maybe I don't worry about it for now. Okay, again, what's the easy case? Simple case. So no page already mapped, for example, because they're talking about all this stuff. Like if there's already a page mapped, do all this stuff. You know, on demand, the page table. So if or page already mapped there, need to TLB flush. If a page was formerly present, so basically we're like overwriting the page. We're like forcibly, we're taking a new page and like forcibly overwriting it at that place. And so how do we tell? I mean, I feel like this is kind of an important function then, page lookup, right? Is this mentioned? It's like it's not mentioned in the TA solution, which is a little bit suspicious. But I kind of feel like that's the first thing I need to know. It's like, okay. Yeah, I don't know. I'm just gonna try it. Struct page info equal page lookup page dir VA, right? And then I'm going to pass in null. I'm not totally sure if I need the page table entry or not. All I'm trying to do is see if page info p equals null. Then that's like the happy path or something. Is that right? Else. Otherwise, there was a page there already. No page there already. I'm a little bit confused why the TA solution didn't mention this function, which seems like it would be kind of useful for us. But okay. Are you able to visualize mentally how all of this happens in hardware? I am having some trouble. I mean, I have some, like, I mean, not mentally, like, I'm referencing this actual diagram, like, all the time. And so that's my visualization of this. Like, I can visualize a bit of the page table structure, kind of, but also I just need to look at this a lot. Prince, yeah. I am American. Yeah. Okay. Oh, 20-second break. Be right back. Okay. Yeah. So let's just do the happy path. What's the happy path? We're trying to insert a page at a specific virtual address. Happy path. There's no page that is already mapped there. Interesting how I talk through implementing my solution. Yeah, thanks. It just helps me. I even do this. Yeah, I think it's a good practice for any programmer. It kind of clarifies your thoughts a little bit. But yeah, again, focusing on the happy path. So, yeah, we're trying to insert a page at this virtual address. I feel like we've like done this already. Didn't like boot map region like sort of do this? It was a very similar task, I think. But but we just had a PA instead of a page info. There's no page there already. What does that mean? If there's no page there already, that can mean a couple of things. It can mean there might be a page table, but there's no pointer to it. Or maybe there isn't even a page table. It's like these two cases. Okay. If necessary, a page table should be allocated and inserted. This thing should be incremented if insertion succeeds. So I think I can already like, I don't know, so like low-key kind of code this part already. You know, if insertion succeeds, this is our success thing. we should be incrementing the ref count, I guess. So this is like there was a page there already. So that's like all this TLB flush needs to happen. What else needs to happen? Page remove on old page needs to happen, right? This is interesting. If necessary. If necessary, on demand, a page table should be allocated. So if necessary, like when is that necessary? I think that it's only relevant for the quote-unquote happy path. Because, okay, in the unhappy path, there's already a physical page there, which means this full chain already exists, which means there must be a page table. But in the what I'm calling the unhappy path. In the happy path, there is nothing there. But it is slightly unhappy if we need to create this. So the happiest path is there is no page that's mapped, but a page table already exists. But it might not. But that distinction might not actually matter. Maybe it's easier to handle the unhappy path first. I think this is how we can detect this, though. I'm still so confused why they say not to. Why they didn't say that they used this, but whatever. Okay, I'm just going to do the unhappy path first because I think I kind of know it. But I just want to again quickly look at the page lookup. So returns the page mapped at blah 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 blah. Is there a path where you have to do nothing basically? I am not sure. At least in the successful path, I don't think so. I think we will always have to do like a little bit. If things start to fail, we can just bail out early with the enomem. But page lookup really just, given the VA, it does the walk and tries to find the PTE. If that doesn't exist, nothing was mapped, so bail out, return, null. Otherwise, get the physical address and convert that to the struct and return that. So I think that's legit. Okay, let's do the unhappy path. So in the unhappy path, let's say there was already a page there. So page remove page info p. CLB invalidate. On the VA though, that's like interesting. Okay, I'm kind of handling this. There was a page there already. Going back to the visualization, there was a page here. We need to so one thing I kind of want to do off the front. PA equals page 2 PA, right? Yes. I feel like we're going to need this. It's like the physical address. So my sense is that we need to find the PTE. but back to our simple. So our plan is handle simple cases first, then handle complications like the edge case. So I'm not even thinking about the edge case, this like whole complicated thing right now. I'm just focused on the main part, and eventually we will get there, but not yet. So what do we know? We know that this thing returned non-null, and so we're going to have to free that thing flush. But I kind of want to do that after I assign into the PTE. So we need to look up the PTE. Pagedir walk VA. And I'm going to say false. TP. Okay. And the neat thing we can do here is assert that it's not null, because or in this part of the code, we've already kind of checked that there is a page there. And so we can be very confident that there's going to be an existing PTE to use. Yep. So we can be very confident. We can be so confident that we're going to assert it. Then, what do I want to do? I want to overwrite. Okay. I have a couple options. Basically, I want to assign. I want to assign this pointer. I want to like make that pointer connection to the new one, but I don't totally know how to do that right now. I need to set these bits. What I was just thinking of is like I could set all like the whole thing to 0 and then just OR in the parts that I care about, but then I would be potentially losing some bits here. But maybe that's what I want to do, actually. This might come back to bite me later, but I am going to do this. Then I'm going to do this. I'm also going to assert, or wait a sec, does that make sense? I was going to assert that the low bits are 0, but like we're guaranteed that by this thing, so I don't know. Probably not necessary. Hey, Corybot24, welcome. So why is this highlighted? PTP. So I'm going to OR in that stuff. I'm going to OR in the perm PTP. Just for a bit of readability. You know, that could also be in one line, but I'm just going to do this. This pointer drilling happened a lot in kernel development. I have never heard that phrase before. I don't know what that means, actually. But we do use pointers a lot, that's for sure. Define an entry in your table and insert the existing page at that position. Yes, pretty much. We find the existing, at least for the code that I'm writing right now, which is only this else, we know there's an existing entry in the table. So yes, we definitely find the entry, and then we insert a pointer to, well, it's kind of like the new page. This is the new page we're trying to point to. And we insert, and like, this is like the PP is like the new page. We're trying to pretend like, you know, this block is like this new page. We are trying to take this arrow pointer and then make it point over to this one instead of the old one. And so that new rectangle is this PP. Using the PP, we derive the PA, and then we set the PA in the PTE. It's a lot of like acronyms and stuff, but like star pointer. I would say hopefully not. I would say hopefully not. I think that's too many stars. Yeah, I would say that's too many stars. More stars than my brain can handle for sure. So usually like 2 stars at most for declaring a variable, but I would never have like like an assignment that's like dereferencing something 5 times. Yeah, maybe occasionally, you know, this double star thing. At most, I've used 3 stars before. I think in my entire life, I've used 3 stars. I can actually find that super quick. I remember it so well to this day. I was working on this library called librequests. Actually, I hope I remember it. And yes, I have my header v append function, which takes in a triple star pointer, and it appends to like a char array or whatever. I don't know. That's the most I've ever used in any C code I've ever written. Yeah, so we assign into this thing, and why am I getting these fuzzy things? Too few arguments. Oh shit. Page dir. Also, I guess here, right? Okay. So for me, it just felt a little bit better to do this whole thing first. Like, reassign the pointer to point to the right place, and then like take care of destroying this old page and flushing the TLB. I'll group this all together. I've done so much coding today, and I literally haven't run it at all. I'm so nervous for when it's time to run it, and we're already kind of out of time. But I do want to try to at least sort of finish this if I can. So that was the unhappy path. That was the unhappy path where something already existed, and we needed to like evict it, kind of. Any tool to find any possible leaks? No. No. Maybe someday, but also I don't know if there's such good tools for doing that for kernels. It's so custom. It's not like a user space program where you just have like malloc and free and stuff. It's like all this it's just like custom functions. So that's the unhappy path. We evict this thing. We have our new thing. We determined that it's the unhappy path. We found this thing. We pointed over here, and we destroyed all this stuff. And then we bumped the ref, counted, and returned 0. Thoughts on AI? Yeah, I think that's a little bit too detailed of a question right now for me. I'm trying to super focus on writing this code right now and start taking like all my brain power. So in the happy path, nothing was there yet. So that's happy because we don't need to evict anything. We don't need to like flush a TLB or anything like that. What we do need to do is get this thing, and in this case we're going to say true, because actually in this case we're actually open to it being created if needed. Okay, so The situation here, though, is we know that there was no physical page. 1 second. I just want to quickly check one thing, though. How can we be sure? Like, so for any, so basically, if we know that there is some stuff that's pointing, we know there's a pointer here, basically. If there's a pointer here, that's how the code continues. So, and so if we're in this part of the path, we know there is, well, in this thing, it wasn't even a PTE. This was that kind of sketchy thing. Yo, thank you for the follow, or for the subscribe, Albs. I'm like getting a little bit confused. But, okay. Okay, back to this. So, in this case, so we know this does not exist. It's possible this thing doesn't even exist. But in this single call, it will create this if it didn't exist and return us this thing, which is nice. And then, I mean, I kind of think we're doing the exact same thing. It's kind of bad to copy the code. 20-second break. Okay, a little bit bad to copy and paste the code like that. And actually, this is not necessary. We don't need to zero anything out. So in this case, we just get the page table entry pointer and or in our bits. I guess, I mean, I kind of want, actually, I want to assert that PTE. Well, it's like, I don't know. I was going to assert that it's 0, but, and actually, wait a sec, I don't even know if that's right to be ORing in the bits like this, now that I think about it, because because ORing will only ever add bits, but it will never remove a bit. And what I want to actually do is like totally overwrite the bits with my new stuff. So maybe actually I do. I think that might have even been like buggy in previous code that I wrote today. To not like have any bits leak, like retain old bits by accident, I think. But let me look for places. Oh no, rip. I am not sure. So I'm pretty, yeah, I mean, even this, I'm not even sure. So this is like, I mean, at this point, this is like kind of old code. Page directory, so. Okay, in this case, it's fine because we, allocated all zeros. So we can be confident about that. In this case, I'm not so sure. Where did this thing come from? Okay, in this case, am I writing my own kernel? Not really. I am following this MIT class. But I am writing like a kernel, I would say. It's just not totally my own. Okay, wait. I was trying to tell if this is correct or not. Linus 2.0. Maybe not quite. If you look into this like world of people writing their own operating systems, there's actually so many people that are doing it. I mean, they have like such impressive things they've built. Maybe one day for me. Not yet. Is this safe? Is this so? You know, I think I don't really think it is safe. I think I need to be setting the bits to 0. Because I think ORing is not. ORing only works if you can OR bits into something that's like a blank slate of zeros, and that works. But if you have like a bunch of ones there already, and if you have like 0 0 0 0 0, and you have like this number, ORing that is like that's going to produce exactly what you want. But if you had some like weird thing like this, I don't know, and you tried to OR in that same thing, like you're going to get all ones. What I'm trying to do though is enforce, like hard write this into the memory. And that's not what's happening if there's like lingering bits in there. So what I need to do is first zero out things, and then I can OR it in. Maybe there's other ways of doing that, but zeroing out is kind of the easiest. And then I have these things that I wrote. Okay, that's pretty much it. So I guess I can kind of assert their entry copy equals 0. Is that true? Page right. This thing. Wait a second. I'm actually not sure. No. Wait. No. No. Okay. I'm not. That's wrong. It's not true that. Well, I actually think. Pointer equals. I think I might need to do this too, actually. Any place I'm like trying to assign these fields of the entries, if I was originally using an OR equals, I need to be making sure that it's a blank slate of zeros before I do that. I don't know, there might be better ways of with using more clever bit stuff or whatever, but I kind of have a sense that that's important. So with that little detour, I'm going to come back to what I was originally doing, which is the happy path, in which case, right, this thing does not exist, which is nice. We checked that, and then therefore we do a walk and get a pointer to this thing. We forcibly, I mean, not forcibly, but we like, we do whatever it takes to make that happen, including allocating a new page table if necessary. And then we take the pointer, zero it out, and then add in the stuff we want to, like the physical address portion of it, as well as the permissions or PTE. And then, so if we've done that, we've successfully pointed this thing here at the page. You know, we really did it. And then time to bump that ref count on the PP. You explored creating your own language for fun and learning purposes. No, I have not done that yet. First, I'm focusing on creating my own OS for fun and learning, and then maybe later my own language. But I'm not as interested in languages, to be honest. So I'm happy to use other people's languages that they write. But who knows? Yeah. Hey, Ankit. Okay, I'm trying to end the stream pretty soon, but I'm just I won't have time to run the code. So it's very I spent this whole stream writing code. I literally didn't even run it once, because in order to run these checker things to make sure I did it correctly, I needed to have all of these things implemented, which it took me the whole stream to do. So I haven't been able to run it, and I'll probably just be spending the entire next stream debugging it. But lastly, corner case. Make sure to consider what happens when the same PP is reinserted at the same virtual address in the same page dir. Sheesh. I don't know. What does that mean? The same PP is reinserted at the same virtual address. Back to the illustration. We have a PP. And so in this case, I guess, can I make that transparent? Okay. We have the PP. It's already there, and we are trying to reinsert it. I do not understand that situation. When the same, I'm also not handling this thing. I need, where do I fail to? Oh, wait a sec. This thing can fail. Shit equals null. Okay. Right, pageWalk for the most part is going to do what we wanted, but we're passing true, but it's possible for it to fail. And then we're going to propagate, sort of, if that fails. Go to null and return no mem or something like that. Okay. But what about this thing? The same, it's reinserted. I don't even understand what that. I feel like actually, Ismail, that's like the code. That's like the case where nothing needs to happen. In that case, everything's the same. It's the same. Like we have a physical page. We have a physical page that already exists, and we're trying to place it at the same place it completely already is. So no TLB flush needs to happen. No page table activity really needs to happen, although it's possible. Maybe the permissions changed. Maybe the permissions changed. So how would our code handle this right now? So we would look it up. We would be in the unhappy path. I don't actually like it is a corner case, but I'm wondering if the code already handles that. Make sure to consider what happens when the same PP is reinserted at the same virtual address in the same page. In that case, okay, just from the top, PP, you know, convert that to the PA. Page lookup. So we're going to get the PA, and it's going to be non-null. We're going to go here. We're going to walk and find this thing. It's going to legit exist. We are going to zero out this thing. We're going to reassign the PA, which is going to be the same place it already points. Wait a sec, is that right? Yeah, the same PP, so the same PA. So it's basically not going to change these bits. Wait, am I doing this? I'm doing this like pretty wrong, I think. No, wait, what? No, never mind. I got confused. VA is used for these lookup functions, but yeah, at the same virtual address. So it resolves to the same PTE as last time. And we set, so this basically isn't doing anything. This might be doing something. It's possible we're changing the permissions, in which case we just do it. And then what? Ah, page remove. That's the thing. In that case, we don't want... in that case, we do not want to do this. That's where it comes in. Case. PP is the same. We don't want to page remove or even TLB flush maybe. Yeah, anime texture. Yeah, like Ismail said, I am just following this course, this MIT 6828, but the 2018 version, not the modern one. So, and how would we detect this? We would detect this by seeing bool. Do I even have bools? Bool is not in C. Yeah, bool is only here because we equals page info p. Okay. Also, what about this? Can this be const? Not sure. Maybe not. Okay. But maybe I can put this all the way down here. Same PP. Okay, I don't know. Why don't you handle this at the very top so you don't have to worry about deleting the page? I'm not sure I understand. Not sure what you mean by very top. Maybe you mean up here? Because I still want to maybe change the permissions, which would actually require a TLB flush. now that I think about it. I think, I'm actually not totally sure. What, like, try not to distinguish this case in your code, as this frequently leads to subtle bugs. There's an elegant way to handle everything in one code path. I don't know. I have definitely more than one code path. Do we need to... Yeah, traversing the entire function, doing no operation except for the last one. Yeah. Shivang, yo man, you joined. I'm about to sign off actually, but it's, yeah, long time no see. Great to see you. I am just debating what to do. I think. I mean, worst case. Okay, I'm a little bit unsure. But yeah, I don't know. I'm pretty scared if this code is like wrong or whatever. It probably is in a bunch of ways, but I don't know what elegant solution there is, but I think I will find out next time. Yeah, I'm gonna bring the stream to an end. Unlucky. How's the progress been? It's been good. I've been writing a lot more code every single time, Shivang. Like, I've been continuing to go through these exercises, and every week I'm able to write a lot more code and understand things a lot better. So the streams are definitely way more exciting than the ones you were watching like weeks and weeks ago. I will say that. And so, yeah. So I'm going to end the stream. Thanks a lot for watching, everyone. Join my Discord if you want. I'll post the link here quickly. My palm tree timer just went off. I'll post the link. Yeah, if you dig what I'm doing, would appreciate it if you give me a like or a subscribe or a comment or anything like that. Would be awesome. And otherwise, I'll see you next week. Thanks a lot. Have a good week. Bye.